Hello, this is Team Reacher, and this is the Vv&T presentation for the ANSA CFD test. I am Brian Shi, the financial lead and aerodynamics lead here in the top middle. So today we'll be talking about the ANSA CFD test. I'll be using ANSYS Fluent as a CFD solver. So CFD solvers model the fluids as it flows around solid bodies in terms of external flows, but it can also be used to model flows inside the bodies for the case of internal flows. So CFD is useful because it can give us a high resolution image of flows in terms of the direction of the flow, the force they produce, and etc. These are in some ways more useful than experimental results, which can only take point measurements at a series of locations, whereas CFD can give you like the field, uh, like flow patterns in the entire field. So the objective of this test is to kind of verify the results from the vortex loss models that was used for flight stream and AVL. But more importantly, we kind of want to ensure that our wing can produce enough lift at low speeds and high angles of attack. Something else that it can help identify some design features that we might want to change because they're producing, for instance, too much drag, or maybe want to change other design features in order to increase the lift of our design. These are all kind of meant to meet some of the drag requirements that our plane can, first of all, be capable of STOL or short takeoff and landing, because we kind of want to take off from the water or when it's being hand launched. In both these cases, we want the plane to produce lift as quickly as possible. So for the experimental setup, a lot of this was done at Hunt Library on a Windows machine with ANSYS installed, which was my laptop. So for the procedure, a model of our UAS, the Hero 1, was created, in this case, in OpenVSP, and then imported into SOLIDWORKS. In SOLIDWORKS, the model was then refined and cleaned up and stuff, and then from there, it was then imported to ANSYS to create the flow domain. So I chose the turbulence model of K omega over Splart because the K omega provided better turbulence modeling than the Splart model. So for the boundary conditions, the plane was set at a variety of angles of attack from 0, 5, 10, 15 to 20 degrees. And then it was also modeled at various airspeeds from 12, 14, 16, 18, and 20 meters per second. So these 25 total cases, I believe, would give us a good range of the performance of the aircraft. And then after the ANSYS solvers converged, post-processing was done to evaluate the forces, the lift on the model. So this is the CFD domain. So it is 32 feet tall, 16 feet wide, and then 50 feet long. It was made this big to ensure that the walls wouldn't interfere with the solution at all. This front left wall, where this front left is the inlet, the back right side is the outlet. Inlet is where I specified the velocity. And then the top, back left, and bottom were walls, were slip walls, so they were specified to have no shear. And this front face, this big front face is a symmetry, which kind of helped the computational time because it basically cut the flow domain in half. And then the body of the UAS was specified as a no slip. So this is kind of a close-up of the mesh. As you can see, there's a lot of cells and nodes on the surface of the body of the aircraft. I believe for this case, each of these edges was specified to be around 0.05 inches. So here's some metrics to use for the mesh. So for the averages, the aspect ratio was 1.84, the skewness was 0.23, orthogonality was 0.77, element quality was 0.84, which are all pretty good. However, it should be noted that for the worst case, the aspect ratio was 13.19, skewness was 0.94, orthogonality was 0.112, and element quality was 0.16, which isn't great. However, given that our solvers still converged, I don't believe these played a huge role in the overall solution. Now, I'll be talking about some of the results from the test cases. So, first let me explain the table a little bit. In the bio table, each row kind of represents the angle of attack, and then the columns represent the velocity. And the values inside each box represent the lift for the given angle of attack and velocity. The color coding just kind of shows a bit of a gradient where the higher the velocity and the higher the angle of attack, the more lift that's produced, which is within expectations. This also kind of shows how if we expect our aircraft to weigh around 20 pounds, we're going to be around 13 meters per second before we will produce enough lift. Um, and then, sorry, the second table is showing the coefficient of lift. As you can see, the values are pretty consistent across the rows, which just shows that velocity doesn't play any role in coefficient of lift, which is what we expect. This is a plot of the first table. So as you can see, increasing with velocity increases lift regardless of the angle of attack. However, the lift kind of peaks around 15 degrees angle of attack at each given velocity. One way to read this plot is that if we draw a line across 20 pounds of lift, which is where it equals the weight of our aircraft, we can kind of see what angle of attack we need for each given airspeed. So this is the plot of this second table. Kind of shows what I talked about earlier, where there's close agreement between each velocity on the performance of the airfoil. And it also shows that at low angles of attack, the ANSYS has very close agreement with FlightStream, which makes sense since FlightStream is a vortex lattice, which doesn't model turbulence, but ANSYS does. So the more turbulent the airflow, the more difference there's going to be between the two cases. Now I'm going to hop into ANSYS Fluent instead of this to show you some of the actual contours. So this test case is, I believe, 5 degrees angle of attack, and I believe 18 meters per second. And as you can see, the flow is very well attached to the wing and the tail. There seems to be little to no flow separation at all, except I guess here in the back of the fuselage, where there is some turbulence because of this kind of bluntish back end. Well, it should be noted that this design in particular was kind of chosen not for aerodynamics, but in order for our plane to be buoyant. So we kind of chose this as a good compromise between having a good center of buoyancy and good aerodynamics. And just another angle kind of showing you the swirling of the streamlines in the background. However, now we're going to switch over to, I believe this is 15 degrees angle of attack and 12 meters per second for the airspeed. So as you can see, there is significant flow separation on the trailing edge, trailing half of the wing. However, it's not completely unattached. You can also kind of see this in the swirls, where that really shows the turbulent air. This may be a bit of an issue, since around here is where our aileron is expected to be. However, at least this also shows that for our tail, the flow is still attached, which is good, because I believe or for us in this case, the rudder vaders are the most important things in terms of recovering from a stall. It should also be noted that I wasn't able to figure out how to implement prop wash for these test cases. So this would be more in the case of where our propeller is turned off for some reason, which I don't expect in the actual test flight. So with prop wash, there should be much better attachment here at the wing root, especially. Going back to our presentation. So one of the biggest issues I had was getting a good y plus value. So here on the left, this image kind of shows the y plus contour for the test case, and then the surface area weighted average was 24.09. You can't really see this in the image, but the maximum y plus value was 50, which is, as you can see, kind of here along the tops of the airfoil, where there's higher air speeds, where the air accelerates over the airfoil. I'll talk a little bit more about this at the end, but I believe this y plus value is not perfect, but given the computational power that I had, and given the number of test cases I had, this was a decent compromise. So going to results, the results show that our UAS model met the level 3 requirements, or level 3 requirement that had a stall speed lower than 14 meters per second, or around 30 miles per hour. The test is considered complete, but the biggest challenge I had was getting good y plus values. Some discussion. So the results show that the Hero 1 was able to produce a lot of lift, even at 12 meters per second. And then I expect the stall speed to be around 13 meters per second, or maybe 28, 29 miles per hour, which is really good. So this kind of shows that the large wings and that's a typo, should be NACA. The NACA 4412 airfoil contributes significantly to how much lift our wing could produce, and this contributes significantly to the STOL performance of the aircraft. These test cases also showed that at 20 meters per second, or around 45 miles per hour, the wings could produce as much as 3 Gs of lift, which is around 60 pounds of lift. This might be useful in the case where, for instance, our plane wanted to do a high G turn or something. So the biggest limitation, the biggest challenge I had was, again, the y plus values was 24.09. This is not great considering the optimal y plus value is below 1. However, for 25 test cases, and like on average, it was 15 to 20 minutes per test case. I thought 24.09 was good enough. However, if I do redo it, I definitely would create a denser mesh so that y plus value would be below 1, and then redo all these tests. However, I do believe the solutions won't vary significantly from what I currently have. And that is it. Thank you for listening to this Vv&T presentation. Thank you.